As far as bang for your buck, it's hard to get more use from a simple concept than what we'll talk about in this video. I'm not talking about MO theory or valence bond theory or even ligand field theory. Those are very useful, but you can easily spend a semester or more trying to master them. I'm talking about a concept that will help you to understand chemistry more deeply across the periodic table that you can learn in a short video. A fundamental idea you've probably never heard of that explains why organic chemistry looks the way it does, why NH3 inverts rapidly while pH3 doesn't, why lanthanides all have similar chemistry, why ligand fields in the first row of the transition metals are smaller, and many other chemical facts across the periodic table. It's so fundamental I feel like we need to cover it before I discuss many other things because it's easier if I can point you to a video on the topic. So here is one of the maybe most important chemical effects that seems to be ignored: primogenic repulsion, or the primogenic effect. I'll quickly cover a couple of important facts about atomic orbitals to start off, which will lay the foundation we need to understand the effect. First, we need to do a thought experiment. Let's just think classically for a minute about how large you would expect an electron orbit to be depending on the angular momentum. Let's think of an electron circling the nucleus like a ball on an elastic string. What would you expect as you increase the angular momentum? As we swing the ball harder, we would expect the string to stretch, making the orbit larger. Since the force holding the electron and nucleus together is coulombic and the charges are constant, the only variable is the distance. If we increase the angular momentum, we expect the distance to increase, weakening the interaction with the nucleus and increasing that orbital radius. Remember that there are four quantum numbers: the principal quantum number, which is given the symbol n. There's what's called the azimuthal quantum number, which is related to the orbital angular momentum and orbital shape, which is given the symbol L. There's the magnetic and spin quantum numbers given the symbols m sub L and m sub S. In any atom, these give the address for a single electron, and only one electron can have that address. The principal quantum number gives the shell. These are integers, n equals 1, 2, 3, 4, etc. The azimuthal value gives the shape of the orbital. The values available are determined by the shell. L equals n minus 1, n minus 2, n minus 3, etc. down to 0. We give these symbols that came from spectroscopy. For L equals 0, we give the symbol S for sharp. L equals 1 is P for principal. L equals 2 is D for diffuse. L equals 3 is F for fundamental. After that, they're alphabetical, so the next is G for L equals 4, although we don't have any elements with G orbitals in the ground state yet. The magnetic value gives which of the orbitals of that shape the electron is in. Those available are determined by the value of L, so that they are integers from m sub L equals negative L to 0 all the way to plus L. Instead of referring to them as m sub L equals whatever orbital number, we sometimes give them a direction by taking linear combinations. For example, if you have 3 p orbitals, the principal quantum number is n equals 3. The p orbital with m sub L equals 1, 0, and negative 1, so p sub 1, p sub 0, and p sub negative 1. These can be redrawn by taking linear combinations to give px, py, and pz, which are maybe more familiar. Similarly, for the d orbitals, you have n equals 3 and m sub L equals 2, 1, 0, negative 1, and negative 2, which can be redrawn as an alternative orthogonal set: dxz, dx, dyz, dxy, dz squared, and dx squared minus y squared. The spin gives whether the electron is spin up or spin down inside of that orbital, so m sub s equals plus 1/2 or negative 1/2. As the azimuthal quantum number L increases, so does the angular momentum. If we were in the same shell, we would expect that the orbitals would get larger with increased angular momentum. For example, in the n equals 4 shell, the orbital should get larger as 4s is less than 4p, less than 4d, less than 4f. In fact, the orbital angular momentum for these are 0, square root of 2 h bar, square root of 6 h bar, and square root of 12 h bar, respectively. In general, this expectation of larger orbital size with higher angular momentum isn't met for a variety of reasons, and we'll talk about one of those reasons in just a moment. The second property of atomic orbitals we need to discuss is that they are orthogonal, meaning they have no net overlap with one another. They can have some constructive interference where the phases are the same and destructive interference where the phases are different, but these precisely cancel to give 0 net overlap. This is obviously the case when two orbitals you're looking at have different angular momentum. If you look at an s orbital, m sub L equals 0, and a p orbital, m sub L equals 1, on the same atom, It's easy to see that the amount of constructive interference and destructive interference exactly cancel. Orthogonality must extend to orbitals in different shells with the same angular momentum, which is where things get interesting. For example, 1s and 2s orbitals have the same general shape, spherical, so they are orthogonal due to their nodal structure. The 1s orbital has 0 nodes, in other words, its phase is the same throughout. We'll say it has a positive phase and isn't shaded. The 2s orbital has a radial node, a place of 0 electron density where the orbital switches from positive phase to negative phase, so shaded to unshaded. These are orbitals on the same atom, so we put them on top of each other. Being orthogonal, the constructive interference, where the phases are the same and overlap, has to equal the destructive interference, where the phases are different and overlap. The 3s orbital has 2 radial nodes and has to be orthogonal to the 1s and 2 orbitals, and so on. Every new s orbital has another node that has to fit together just right with the other s orbitals. Here's the important bit. The 1s orbital doesn't have to be concerned with being orthogonal to anything. It can contract towards the nucleus to lower the energy of its electrons and remain orthogonal to any other orbital. However, the 2s orbital has to be of the appropriate size to be orthogonal to 1s. It's restricted by the size of the 1s orbital. When the 2p orbital appears for the first time in the first row p block elements, like carbon, it doesn't have to be concerned about being orthogonal to 1s or 2s, because it has a different angular momentum. It will automatically be orthogonal. It can contract towards the nucleus to stabilize as well. 3p has a radial node, however. It has to stay orthogonal to 2p, so its size is set by the size of the 2p orbital. What we say is that every time there is the first appearance of an orbital with a new angular momentum in the periodic table, that orbital will be somewhat smaller than expected, because it can lower the energy by contracting. In other words, the 1s, 2p, 3d, and 4f orbitals will be smaller than expected. On the other hand, orbitals beyond these undergo a primogenic expansion due to the lower orbitals of the same symmetry. They have to be a specific size to remain orthogonal and can't contract to lower their energy. Why is this important? I'll give a couple of examples where the primogenic effect influences chemical properties. Let's compare a first row p block with a second row p block molecule. How about water and hydrogen sulfide? The molecule with the first row element, water, has a larger HEH angle at 104.5 degrees, while the heavier derivative has a smaller angle at 92.1 degrees. The larger angle in water indicates more sp mixing, while the angle in SH2 near 90 degrees indicates that almost pure p orbitals are being used for the bonding. This is a general feature when comparing first and second row compounds with lone pairs and substituents. For example, NH3 has an HNH angle of 107 degrees, while PH3 has an HPH angle of 93 degrees. The question is, why? When I was a youngster, I was taught that the reason there was less hybridization below the first row was because the energy gap between the valence s and p orbitals was larger. Orbitals that are closer in energy mix more easily than orbitals that are energetically different. If we look at the energy difference between the s and p orbitals for the chalcogens, here's what we find. The first row element, oxygen, has the largest energy gap, which should make it harder to mix the two to make hybrids. In other words, whatever it is that makes hybrids more common for the first row, it isn't related to the orbital energies. However, let's look at the mean orbital sizes of the s and p valence orbitals. Better yet, let's look at the sp orbital ratio. Based on our previous discussion, the lower angular momentum orbital s should be smaller, so the sp ratio should be less than 1. Here's the data from Waber and Cromer's study. Notice for the heavier elements, sulfur through polonium, our expectations are met with the p orbital being a little larger than the s. So the ratio is 80 to 90%. For the first row element oxygen, however, the s and p orbitals are around the same size. In fact, the p orbital is a little smaller, giving it an s to p ratio of slightly over 100%. The reason for this is the primogenic effect. There is a lack of primogenic repulsion for the p orbital for the first row element. This term was used first in the literature by Pyykkö in 1979, and the reference is in the show notes. In short, the effect is due to the fact mentioned earlier that atomic orbitals must be orthogonal to one another. If the orbitals are of the same shape, then this is done by fitting together their nodal structure. If there is no orbital of the same shape, then the orbital is orthogonal to all the atomic orbitals regardless of size, like the S and P example we showed earlier, which means it can stabilize by shrinking towards the nucleus. In other words, the first time an orbital shape appears, it tends to be relatively small. This affects the size of the 1s, 2p, 3d, and 4f orbitals. All these orbitals tend to be smaller than one might expect. What does this mean for the chemist? It means a tremendous amount. It explains many different effects in chemistry that you might spend entire courses exploring. For the main group, it means that the 2p orbitals shrink to about the same size as the 2s orbitals for the first row, which allows good sp hybridization. In other words, it explains all of organic chemistry and why sp hybrids are so prevalent for carbon. It explains why organic molecules have the shapes they do and react the way they do. For the transition metals, the small 3d orbital size leads to lower bond energies in the first row and smaller ligand fields relative to the second and third row metals. So it explains why you sometimes get high spin complexes of the first row, but not of the second and third rows. For the F block, it explains why the chemistry of the lanthanides are all about the same. The 4f orbitals shrink below the size of many of the core orbitals, making them practically inaccessible for bonding. So changing the number of electrons in these orbitals doesn't dramatically change their chemistry. It also explains why the lanthanides are so valuable for their magnetic properties. This is really just the tip of the iceberg as far as where this effect pops up in chemistry. It really is the most important effect you've probably never heard of in chemistry. Thanks for watching. We make these videos for fun and as a way of giving back to the community. If you enjoyed the video, please subscribe and give us a thumbs up. Really, the best way to support our channel is to watch more videos, and we have quite a few up at a variety of levels. We generate videos as best we can since we have other jobs, so please turn on the notifications button so you don't miss anything. Thanks again.